last week, and will be our topic for the remainder of the semester, is the problem of thinking about light forces on atoms. So, the notion that electromagnetic fields and light carries not only energy, but momentum, of course, goes back to Maxwell and the energy stress tensor. So we know that electromagnetic fields carry energy, and there's a flux of energy related to the Poynting vector. And there is a flux of momentum that is dependent on the flux of energy divided by the speed of light. So these light forces that we started to discuss kind of come in two flavors. There's a force that is dissipative, and a force that is conservative. The dissipative force is what is responsible for ultimately heating and cooling, whereas the conservative force is associated with trapping in the optical field. So, why do we care? Why is this an important topic? And it's been an extremely important topic in modern atomic physics. I mean, the whole field of atomic physics has moved almost completely in this direction in thinking about atoms that can be cooled and trapped. Well, I mean, historically, the problem, the thought about cooling in particular, well, trapping, first of all. It's hard to trap an atom. An atom's flying around pretty fast, and at least a thermal atom, and especially a neutral atom. I mean, the first trapping experiments that were done with atoms were not done with neutral atoms, but they were done with ions. So trapping a charged particle is a lot easier to do, kind of. So it depends what parts are easy and parts are hard. But in principle, we can get started a lot easier with ions than with neutral atoms because, of course, ions are charged. And you can exert much stronger forces on charged particles than you can on neutral particles, just through electric fields. Once people started to trap ions, one of the things that was considered, well, when they're trapped, can we cool them? Why do we want to cool particles? Well, cooling is important if we want to do precision measurements. And a big part of atomic physics is about precision measurements. Some of the reasons we care about doing precision measurements are for fundamental physics. For example, we talked at the beginning of the semester that one of the very central topics in atomic physics is to try to, for example, measure very small forces like the fundamental forces of nature, tests of the standard model, tests beyond the standard theory of electroweak interactions. And in order to do that, we want to make the most precise measurements are possible. If the atoms are hot, it's a lot harder to measure them. So the colder they are, the less they're moving around, the more precise we can measure those atoms. From a technical point of view, those precision measurements, one of the most important applications of that is in the atomic clock. So a lot of the motivation for cooling atoms and ions was to make more precise clocks. In the context of the cesium standard for the second, that neutral atom, what limits our precision with which we can measure the frequency difference in the hyperfine splitting, which is the definition of the second, what limits that is how long we can do the measurement. Because you know there is a kind of uncertainty principle. If I want to measure a frequency, there is a limit to that uncertainty, which is related to the length of time with which we do the observation. So, and a very important motivating fact for trying to cool atoms was in order to, in the context of the neutrals, keep the atoms around long enough in a certain region of observation so that we can make a much more precise measurement of the frequency, and therefore, in that context, make a more precise measurement of the second. A similar kind of thing is true in ion traps. I mean, the ions are around, but they're still vibrating very fast if they're not cold. And that limits, if I'm going to use an ion as my precision, for my precision measurements for doing my clocks, that too is a limitation. So the history of this is quite long, and I meant to bring with me, and I forgot unfortunately, a list of some of the key dates. I can try to remember some of them. You know, I do know that the first, in 1975, there were kind of dual discussions about cooling with light forces. There was Ted Hench and Art Shallow talked about laser cooling neutrals, and Wineland and Itano for ions. There were two independent groups looked at this simultaneously. Around the same time, I think it was maybe 1978, Art Ashkin thought about trapping neutrals in laser beams. Actually, what he was looking at originally was trapping little glass balls, little small particles or polarizable particles, but ultimately thought about this in the context of atoms. But the modern era where things have really gone started in the 80s. In the 1980s, there was a tremendous amount of work thinking about taking these ideas. This was Wineland and others were early pioneers in laser cooling of the trapped ions. But the work on the new tools was much harder, happened a lot later. Well, not a lot later, but a few years later. And some of the key players here were Bill Phillips, our current Secretary of Energy, Steve Chu, and in the theory side, Claude Cohen. And Bill was the first to slow an atomic beam and then trap. And Chu at the time was at Bell Labs. You guys too young to know what Bell Labs is? Bell Labs, you know, it's a sad story about Bell Labs on the great industrial labs and transistor everything. I mean, Steve Chu was there working on, I think Ashton was there at the time. I actually don't remember. It's before my time. But anyway, working on cooling and trapping atoms, and developed what was the first, what we call optical molasses that we'll talk about. How do you spell molasses? Are there two L's in molasses? Is that how you spell molasses? I can't.
There may be one L.
I think it's one L.
One L, two S's? One L, two.
One L, one, I think.
Is that right?
I don't believe it.
I don't know.
I think that
I'm
was-
sure about the L, I'm not sure about the S.
We'll just leave it as such and don't remember. It's terrible. Someone must know. Anyway, so molasses was a kind of, a notion of a kind of sticky, this is optical molasses, sticky optical field for damping atomic motion. And this stickiness, together with magnetic fields, led to what was known as the magneto-optic trap, which is now the workhorse of all cold atom, neutral cold atom experiments, affectionately known as the MOT. In fact, people call the group of atoms that come out of the magneto-optic trap a MOT. I have a MOT, it's this ball of atoms. That's the kind of jargon that is used today. And Cohen, together with Jean Dalibard, who was, I believe, his student at the time, really led a lot of the theoretical foundation. And together, these folks won the Nobel Prize in 1997 for the development of laser cooling and trapping. And soon after this work was done, one had a system in which the atoms were so cold, in fact, they were colder than were originally expected to be. I mean, this was one of the important theoretical contributions of Cohen-Tanucci and experiments out of Bill Phillips' group. So-called subdoppler temperatures that we'll talk about, that laser-cooled atoms became a starting point for evaporation to Bose-Einstein condensation. The idea that you could condense a gas into a Bose-Einstein condensate goes back a longer way. It goes back to Kleppner and Greytak, who were trying to do this with hydrogen gas, with traditional cryogenics. And it was tough. It didn't work. It didn't work, in fact, until after, in 1995, the groups of Carl Weinman and Eric Cornell at Gilla and Wolfgang Ketterle at MIT made the first BCs in rubidium 87 and sodium 23. So laser cooling is really the important starting point to which one can then get to the ultimate super cold temperatures where we see a quantum phase transition to a Bose-Einstein condensate, and then later thinking about degenerate quantum gases of fermions. Debbie Jin at Gilla did this, probably in 2000. I don't know, it was 1990 something, maybe 9. I don't remember exactly when that was. Once we have these ultra-cold degenerate gases, then we can really start thinking beyond just the problems of the interesting problems associated with precision measurements and atomic clocks. Not to denigrate those important problems, but in addition, there is new physics to be gained by thinking about ultra-cold matter. So now, the atoms themselves, the whole atom, rather than just the atomic structure that we've been talking about for the majority of this course, we think about the atoms as the particles, not the electrons and the nuclei, but the atoms in a gas can have properties that we usually think about in the context of condensed matter. Properties like superfluidity and superconductivity and quantum magnetism and the Ising model and all of the kinds of many-body physics that it's typically the purview of condensed matter becomes available once we start getting into a regime where the de Broglie wavelength of the whole atom, not the electron, is big compared to the distance between the atoms. So the wave nature of the whole atom becomes important, and this leads to yet another field of study, and that's the field of what's called atom optics. So instead of thinking about the wave diffraction of light, we can think about the wave diffraction of the whole atom, thought of as a quantum wave. And that too, kind of ties back. In some sense, the atomic clock is an atom interferometer, but it's an atom interferometer that depends on the internal degrees of freedom, whereas we can tie that back and think about atom interferometers which have to do both also with the external degrees of freedom, the motion of the atoms, as well as its internal degrees of freedom. So this is a very rich field, a field that is really taken off in the last 20 years, and it's still accelerating, and the merging between atomic physics and condensed matter physics is becoming more and more prevalent as we have access to thinking about ultra-cold matter and the interactions between atoms that can be controlled in a manner that's just not accessible in traditional condensed matter physics. All right, so we want to now spend our time getting a little bit more quantitative, thinking about these forces, how we can use them to cool and trap. How cold can we get? How big can our traps, how deep can our traps be? All right, so let's get started on that. So, at last lecture, we got started by thinking about this from the point of view of classical physics. And if we thought about this as the force, classical force on bound charges, what we found last time is that if we had an electromagnetic wave with an electric field, function of position and time. Sure, I think I heard my phone go off there. Shut that off. There we go. It's the real part of some amplitude, which might be spatially dependent, but it modulates a plane wave here. Okay? So L here stands for light or laser. This is the wave vector, that's the frequency. There's some amplitude, which depends on the position. Then what we found last time was that the force, time averaged over the rapid oscillations of the field, could be broken up into two pieces. We had a piece that was the time average of that term. And then we had a piece that looked like the time derivative of the induced dipole moment. So D here is the induced dipole moment. And we discussed these two terms had two different physical understandings. In particular, this induced dipole moment, we said this induced dipole moment as a function of time classically was given by the real part of the atomic polarizability times the electric field at the position of the atom. That these two terms broke up into these two pieces that we were just discussing. We have, if I write my complex polarizability as having a real part and an imaginary part, then we had one force that we called the dissipative force. Well, let's start with this one. We have what we call the reactive force. And if we plug this in with this, then what we find is that this is equal to 1/2 E star dotted into the gradient times the 1/2 the real part charging. It's called reactive because it depends on the real part of the polarizability. And we saw that this is a conservative force that is related to the gradient of a potential, which we call the light shift potential. And that light shift potential in this classical model is equal to something we've studied many times now. It's the energy associated with a polarizable particle in the field, which has some electric field strength, electric field E of R. So this is the energy induced in a polarizable particle. The reactive force is a conservative force. Okay. In contrast, we have this other term here, which we call the dissipative force. And if we say that the induced dipole moment here is equal to alpha, the real part of alpha e to the minus I, maybe L2 minus omega R t times the electric field amplitude. Then if I plug this in to this expression, take that time average, we find the following. This is equal to 1/2 omega over c, the imaginary part of the polarizability, times the electric field amplitude squared, times, that's it, right? E squared, times the E sub r here is the direction of the wave vector. So this is called dissipative because it depends on the imaginary part of the polarizability. And that imaginary part, you'll remember, is related to how much power is absorbed by the dipole from the light. And in particular, if we rewrite this, let me divide by 8 pi and multiply by 8 pi. So then when I get is 4 pi omega over c, the imaginary part is alpha. This is what we found last time to be the absorption cross-section associated with that dipole. And this is equal to the power absorbed, or the power incident divided by the speed of light. So our dissipative force is equal to, excuse me, this is not the power, this is the intensity. This is equal to then the absorbed power over the speed of light, and the direction of the force is the direction of the wave vector. This is what we call radiation pressure. this is what classically you would calculate for how much pressure a light wave is exerting on an absorbing body. This is the pressure. This is the effective area presented. It's the cross-section. The pressure times the area is the force. And that's what we call radiation pressure. Okay. So, we have these two kinds of forces. The radiation pressure is what we want to try to ultimately harness to cool. Of course, it also is responsible for heating. So we got to be careful about some balancing between heating and cooling. And that ultimately sets the limit of what temperature you can reach, because otherwise you just cool forever and you get to zero temperature. So some balance of heating and cooling sets the limits of what temperatures we can reach. Whereas the reactive force, which is sometimes, this has other names, this force is also known as the, sometimes known as the optical dipole force. Is conservative. It's not going to give me cooling, but it can trap. It can trap if this produces a potential well, because if my polarizability is positive, then when the intensity is big, if the intensity varies as a function of position, well then I can create a negative potential. Let's say I could create a potential well and use that to trap particles. So, this is our classical description. In order to really get at the heart of the matter and understand the limits of cooling and trapping of atoms, we need to think about the quantum description of this. But we can get a lot of mileage out of understanding the physics of this by understanding the classical picture. So I really urge you to keep this in your head. The basic physics is here. The quantum mechanics will give us additional details that are important, but this classical picture is the foundation of what's going on. All right, so now let's turn our attention to thinking about a quantum description of this. Oh, Lord. Excuse me. All right. At least I don't have the famous little Hitler mustache, which I tend to get every last Don't go like this. All right. So, light forces on atoms. We're talking about a quantum description. So our interaction potential, our Hamiltonian, we can break up into two pieces. There is a piece that I'll say is the interaction with the laser, and a piece that will be the interaction with the vacuum. We fundamentally need both of these pieces because, as we know, it is the vacuum that is fundamentally responsible for the fact that we get spontaneous emission. And it is that spontaneous emission which ultimately gives rise to dissipation of energy. If we didn't have spontaneous emission, we wouldn't have dissipation. So we need to, at some point, think about that part of the problem as well. But our atom-laser interaction, and both of these we will, we'll make the dipole approximation. and think about the interaction with the laser field and the interaction with the vacuum, which is itself an operator. Okay, so if we're not going to get into this in depth, but if we truly wanted to discuss, and this is discussed in the notes that I posted on our website from the Les lectures from 1992, continuity goes into some details, and it's available there for you to read. But in principle, we need to think about the quantum electromagnetic field and thinking about vacuum fluctuations. Okay, now, my electric field in the dipole approximation is acting at the center of mass of the atom. In the case of the atom, that's basically the nucleus. If we're going to be thinking about the quantum problem, in principle, I really should think about the motion of the atom itself as a quantum mechanical object. I mean, I just erased it there, but I talked about the de Broglie wavelength of the atom. What I'm talking about is the de Broglie wavelength of the whole thing, which is basically the de Broglie wavelength of the nucleus. Thinking about the nucleus as being something that has quantum fluctuations or quantum uncertainty associated with its motion. So in principle, we really need to think about the center of mass, which in this case is really the nucleus, because the electrons are negligible contribution to the weight or mass of the atom, as a quantum mechanical object. Of course, the dipole here is related to the relative coordinate of the electron relative to the nucleus. And so, that's E R. So there are two kinds of degrees of freedom here in the quantum problem. If we really want to think about this problem of light forces quantum mechanically, we have what we call the internal degrees of freedom, which have to do with the motion of the electron relative to the nucleus, and what is sometimes referred to as the external degrees of freedom. Which are referring to the fact that external to the atomic structure, there is potentially a well that can trap and forces that act on the center of mass. This is the jargon that we use. So let's look at this in the case where my laser field is itself of the form that we just described. It's a plane wave modulated in some way, like a laser beam. So my electric field, let's look at the atom-laser interaction now in more detail. So if we look at, again, the two-level approximation, we're going to need to return to that soon. Think about that a lot more carefully. But remember, our two-level approximation was under the assumption that our light is tuned very close to resonance and only excites from, say, some ground state up to some excited state, and all of the decays back to that ground state. Okay. Then my dipole operator can be written in this basis, and we've done that before. This then is this is our pseudo-spin. That's our dipole operator. That is the operator that's related to the internal degrees of freedom, right? Couples the orbitals. And then we have the electric field, which we said was the real part of some amplitude as a function of position, e to the minus I omega LT minus K dot R, which is an operator. And then the real part of that means this over 2 plus its complex conjugate. So, what do we have there? In the rotating wave approximation, this is equal to minus h bar, the Rabi frequency, as a function of the position. That's d dot e. And then we have sigma plus times e to the minus I sigma plus So, our atom laser interaction involves operations that act both on the internal degrees of freedom and the external degrees of freedom, right? This operator, we understand that this is associated with absorption. Remember, this is the positive frequency component. This is the part that has to do with absorption. This is the part that has to do with emission, because this takes me from the excited state back to the ground state. So, we understand what sigma plus does, but what is this operator? Well, that's a familiar operator, maybe. Remember, in wave mechanics, the momentum operator is the generator of translations, right? That's to say, if I take the momentum operator and I look at e to the minus I on a position eigenket, I get the displaced K. You remember that? And the position is the generator of momentum translation. That is to say, e to the plus I r hat dotted into p naught over h bar, acting on a momentum eigenket, translates in momentum. Those are fundamental results from wave mechanics, right? So, what is this?
Change in moment.
Right, this is the momentum translation operator. Translating by momentum. So this is a momentum translation operator, which translates me r dot h bar k over h bar hat. So when I am absorbing, going from the ground state to the excited state, I am translating in momentum by an amount h bar k. That is to say, when the atom absorbs a photon and goes from the ground state to the excited state, the center of mass recoils. Like, whoop, a bullet hits it, and the bullet has, the photon bullet has momentum h bar k. So this takes into account the effect of what we call recoil. This is a quantum mechanical description of the atom recoiling because it's absorbing a unit of momentum, h bar k. So, a very important quantity in thinking about light forces from the point of view of quantum mechanics is the recoil. And the recoil momentum is how much momentum does the center of mass pick up if it absorbs a photon? And the answer is h bar omega over c times in the direction of propagation. So, there are two kinds of dynamics that are occurring as generated by this Hamiltonian. One kind of dynamics is the dynamics that drives the internal degrees of freedom through the Rabi frequency and also through spontaneous emission. And it's the internal degrees of freedom that we've been studying in the last number of weeks. We've been looking at how the electrons get excited, de-excite, we induce a dipole moment, and we can relax the steady state and all of that. But in the process of that, in addition, the atoms are absorbing and emitting momentum and causing their center of mass to change according to momentum conservation. Now, before I do that, let's just get a sense of how big this is. So one thing that what one can calculate is what's called the recoil velocity, which is how much velocity or speed does a atom with mass m pick up when it picks up this much momentum. So the recoil velocity is h bar k over the mass of the atom, which we'll call capital M. And how big is that? Well, you just got to calculate it. For a couple of atoms that are used often in laser cooling experiments, this chalk is helpful. Not much better. So for sodium-23, the recoil is 2.9 centimeters per second. In rubidium-87, the recoil velocity is about 3.5 millimeters per second, and in cesium-133, the recoil velocity is about 2.9 millimeters per second.
What speed is this exactly?
So, but the speed represents is if the atom is at rest and absorbs one photon of momentum, how fast would it go?
Okay, it's one photon. That's probably for a certain transition?
Well, it depends on K.
Yeah.
Okay? So K, of course, is 2 pi over lambda. So in each of these, we need to know what the wavelength that we're talking about. Well, I guess I should step back for a moment and say something else. So we made this two-level approximation. When is that a good, is there an example where that's a good approximation? Well, the answer is yes. It can be a pretty darn good approximation when we have requires what's called a cycling transition. So, notice all of these atoms that I just wrote down are alkali metal. They're group 1. Ones we've talked about in our discussion of the atomic structure at the beginning of this course. And in particular, we know from the dipole selection rules that, so the ground states in all of these guys are doublet S1/2s, right? Depending on the principal quantum number. Principal quantum number 3 for sodium, 5 for rubidium, 6 for cesium. In addition, we have nuclear spin. So let's look at sodium. So sodium has a nuclear spin of 3/2. So in addition to the electron fine structure, we also have hyperfine structure. And that hyperfine structure is determined by F. So what are the possible F's associated with this ground state?
1 and 2.
1 and 2, right? Because we can have I plus J, which is 4/2 or 2, or I minus J, which is 1. So, now up here we have excited states. We have, of course, we have the excited P state, which is the first excited state, and you know that we can have the J's either 3/2 or 1/2. And they cause the transitions we've discussed, we call them the D1 line and the D2 line. Let's look particularly at the D2 line. So now what are the possible values of F here? What is J? J is 3/2, I is 3/2. So F can be 3, 2, 1, or 0. Okay, so this is my excited F prime equals 3, 2, 1, or 0. And what I've drawn on the magnetic sublevels, the M's of F levels. So, this of course is an allowed transition, but of course the particular connections of the selection rules that we discussed through the semester also have restrictions not only on S to P, J can change by 1 or nothing, but no 0 to 0. And then F can change by 1 or plus 1 minus 1 or 0, but no F equals 0 to F equals 0. So suppose that somehow the atoms were prepared, and we'll discuss that at some point soon, were prepared all in this state. And I put on sigma plus light. So, this is the only allowed transition, right? Because delta m sub f, if I have sigma plus light, that's of course nothing to do with that other sigma plus you wrote down. Totally different use of the term sigma plus. Here delta m sub f is plus 1, because I have sigma plus light. And everything else, there's no other place I can go. And in fact, if I'm here, there's only one place I can decay. Why can't I decay here? I mean, delta m sub f is 1, that's okay.
Delta F is 2.
But delta f is 2. So that's not allowed. So this is what's called a cycling transition. Because the atom cycles. It absorbs a bit, absorbs a bit, absorbs a bit, absorbs a bit. There's no place else it can go. If I have exactly this polarization, of course, if I have a little bit of other polarization, well, you know, I can go from here to here, and then I'd be stuck there, and then I better pump it out if I want to get it. So that's a different story. But if I have exactly sigma plus polarization of exactly 2, and that there's no place else, and that's a cycling transition. This is the reason, as we'll discuss, why it is the alkali atoms where the majority of laser cooling and trapping experiments are done, because of the simplicity of the atomic structure, because of this hydrogen-like atomic structure of the group 1 elements, there exist these strong transitions which are cycling transitions. Okay? So, the wavelengths associated with these transitions, also the mass, which is given by here, the number of atomic mass units, and then the wave number depends on the wavelength. For the D2 line of cesium, the wavelength is 852 nanometers. For rubidium, 789?
780.
780, thank you. People who know these things. And this is 589, I think. So sodium. It's yellow. It's a dye laser, it's terrible. God, it's embarrassing I don't remember that, but whatever. Okay. So you plug in those wavelengths and these masses, this is the speeds. So, we have recoil. And the recoil momentum then determines an energy scale through the recoil velocity through which the center of mass changes. So there's 2 time scales associated with the dynamics, 2 important time scales associated with the dynamics that are driven by this atom laser Hamiltonian. What we have done to date is we've kept the atom fixed in space. We said the atom is somewhere, and then we were driving it, and we were asking it Rabi flopping, and we had damp Rabi flopping, and we had steady state. But we know that in the process of doing that, the atom will move. So, do we have to take into account the complicated dynamics, the quantum dynamics, that couples the internal and external degrees of freedom? Right? I mean, there's a kind of entanglement, maybe, between internal and external degrees of freedom. That sounds like a giant mess. Sounds hard, maybe fun, but depends what your definition of fun is. So, on the other hand, if the atom, if these time scales are very different, if there's a separation of time scales associated with the time scale to which the internal degrees of freedom come to steady state versus the time scale over which the atom is forced to move due to recoil, Well, then we can basically treat this kind of adiabatically. At every position, there's some interaction, then the atom moves. But I don't have to think about the quantum dynamics that are, in some sense, coupling the quantum motion of the center of mass with the quantum motion internal to the atom. So, an important simplifying assumption is the separation of timescales associated with internal and external degrees of freedom. What are those timescales? Well, the internal degrees of freedom steady state reached in some time scale called the internal time scale on the order of the lifetime, 1 over the natural line width. That's the damping time associated with the internal degrees of freedom. The external degrees of freedom well, the external time scale here is associated with a different energy scale. And that energy scale is what we call the recoil energy. It's the energy associated with the kinetic energy of the atom when it recoils due to absorption of h bar omega. So the ratio is the ratio associated with the recoil energy compared to h bar gamma. And we want this time to be much, much, much longer. I have it backwards. Now it makes sense. Gamma uncertainty principle. We want this time scale to be much, much longer than this time scale in order for us to separate out the dynamics. Is that true? Well, let's take a look. What is the recoil energy? Well, the recoil energy is defined as this energy scale that we just described associated with atoms moving with that much momentum. That's the definition of the recoil energy. And K here is the laser wavelength, or wave number, excuse me. Okay, so again, we just have to plug that in. What we're interested in here is this ratio, which I will write as h over gamma over 2 pi divided by the recoil energy in units of Planck's constant without the bar. That's the usual way it's done. So we typically talk about the recoil energy in some number of hertz, right? Or per seconds. So we just have to plug that in, and here are the numbers. I remember it for cesium, but I don't remember for anything else. Oh, well, I guess we should get a little bit of a sense, how big do we think this is, just from, you know, we should have some physical intuition. How big is this energy? Well, let's think about this. How would we do it? I mean, if we didn't have a calculator, we didn't have an iPhone which had a calculator on it, what the heck are we going to do?
Doesn't it have to be h bar omega because that's the energy in drops?
There is another energy here which is related to the mass of the it's another scale here. If it only depended on the wavelength, you're right, there's only one energy. But this is a ratio. The recoil energy, if we look at this.
I mean the ratio.
What's that?
You mean what's the ratio? Okay.
What I want to know is, what is this energy? How big is it? How many electron volts or joules or whatnot? Well, we can look at that. That energy can be seen as the ratio, as Cornelius. There is H bar. If I write K as omega over C, then this ratio is the ratio of the square of the photon energy to the rest energy of the whole atom. So it's going to be a tiny energy, right? How big is the energy of a photon? An optical photon. In any units you like. Do you have a feeling for that? The energy of a photon is about a half of an electron volt. So this is about a half of an EV. And what about the mass of the atom? Yeah.
It's a few electron volts.
Right, so the mass of the proton is actually a giga electron volt. So it's a billion. And so, and this of course depends on the atomic number.
It's nano until something between nano and micro electron volts.
It's going to be smaller than that. Smaller than that. Because we have all these factors of 2 around here, and we also have the atomic number. Now, if it's hydrogen, yeah, it's a lot. It's closer to micro, maybe nano EV. But let's just take a look. So this is like square to, let's make that 10. It's like 10 to the minus 1, 10 to the minus 9 over the electron volts. Okay, so that's on the order of pico EV. Few, maybe a fraction. It depends. This is for visible light. If we start getting into the IR for cesium and rubidium, the energy is smaller, by about a factor of 2. And then you square it. So, turns out the recoil energy is fraction of pico EV. Okay? Yeah?
I still don't understand where the energy goes, because isn't the photon absorbed at the process?
The photon's absorbed.
Okay, where does the energy go?
Right now, so the energy, the atom has been excited.
Okay.
So part of the energy is going into the excited state. But in addition, the atom is moving. Now, there is an important subtle point that is implicit in your question, which is that the resonance energy is shifted because of the fact that the atom recoils. That's called the recoil shift. So in order to actually exactly put, if the atom was at rest, and I want to then put it into the excited state, the frequency at which I should tune my laser is not just the difference of the energy eigenvalues without the motion. It shifted slightly, and it shifted slightly by this amount of the recoil. The atom is moving, as we'll discuss. Of course, there's a Doppler shift, and that's yet another story. Okay, excellent. So the atom absorbs, it goes into this excited state, and it's moving. Its inner mass is moving, and therefore picks up this amount of energy. This is pico-electron volts. This, if you turn that and divide by Planck's constant, is on the order of 10 kilohertz. So, we need to expand out this poorly organized chart. Let's write it out anyway. So in sodium, first of all, the natural line width is on the order of 10 megahertz. In rubidium-87, it's on the order of 6 megahertz. And the natural line width for the D2 line in cesium is on the order of 5 megahertz. So it's over a few megahertz. Whereas the recoil energy in units of Planck's constant for cesium, I remember it, because that's the atom I work with, it's 2 kilohertz. And then I don't know the others. It's about 3.7 kilohertz in rubidium, and in sodium, it's 25, because it's lighter kilohertz. So, one of the things that we learned from this discussion so far is that for these atoms with this kind of wavelengths that are, 500 to 800 nanometers, the recoil energy is much, much smaller than h bar timescale, which means that the timescale associated with the center of mass motion of the atom is much longer than the timescale associated with the driven internal dynamics of the atom. And because of that, in this regime, if we have atoms that are kind of freely moving, we often, until we start getting into very cold temperatures where the wavelength matters, but for the atoms that come out of, say, a thermal oven that we want to then cool and trap, we can forget about the fact that this is an operator and just replace it by its mean value. And treat the atom's motion classically. We treat the internal degrees of freedom still in terms of the quantum mechanics of absorption of emission, but we treat the atom as a kind of billiard ball. So, with that said, then we can calculate the force thought of in this semi-classical regime. So the semi-classical force is the field atomic motion classical. The internal degrees of freedom quantum. We can then write down a force operator. The atom laser force operator, the operator acting on the atom, is then equal to and from this, we can determine the expectation value of this operator, where the expectation value is related to the particular state of the atom. So this then is equal to there should have been an over 2 here. Because of this over 2, I lost it. what this then is equal to is times twice the real part of rho GE in the rotating frame. So, we then have to decide what the state of the atom is. If we want to look at this force in steady state after the atom has reached its transients, well, we know the steady state solution. Firstly, we rewrite this in terms of the oh, you know what? I made a big mistake here. This is not the force. This is the potential. So the force, the average force, is minus the gradient of this. And if I write this then is equal to h bar over 2, the gradient of the amplitude plus k plus complex constant. So what I did is I took the gradient of the amplitude and I took the gradient of the phase. The gradient of the phase is I times k. And then we have to write this plus its complex conjugate, which came from this term, which then gives us the real part of this complex number. We'll pick this up again next time, but let me just conclude by saying we'll see the following results. There is a term here that has to do with the gradient of the amplitude, which will depend on the real part of rho G, which is the real part of the atomic polarizability. And there will be a term that's in the direction of the wave vector that will depend on the imaginary part of rho G, or the imaginary part of the polarizability. And these are exactly what we saw classically, related to the gradient of the amplitude, or the gradient of the intensity, and the term that has to do with the absorbed power. And those two forces are what we saw classically, what we call the reactive force, or the optical dipole force, and a term that is radiation pressure. And we'll return to those, look at them in more detail next time. All right? Good enough then. We'll see you last week, and will be our topic for the remainder of the semester is the problem of thinking about light forces. So, the notion that electromagnetic fields and light carries not only energy, but momentum, of course, goes back to Maxwell. and the energy stress tensor. So we know that electromagnetic fields carry energy, and there's a flux of energy related to the Poynting vector. And there is a flux of momentum that is dependent on the flux of energy divided by the speed of light. So these light forces that we started to discuss kind of come in two flavors. There's a force that is dissipative and a force that is conservative. The dissipative force is what is responsible for ultimately heating and cooling, whereas the conservative force is associated with trapping in the optical field. So, why do we care? Why is this an important topic? And it's been an extremely important topic in modern atomic physics. I mean, the whole field of atomic physics has moved almost completely in this direction in thinking about atoms that can be cooled and trapped. Well, I mean, historically, the problem, the thought about cooling in particular, well, trapping, first of all. It's hard to trap an atom. An atom's flying around pretty fast, and at least a thermal atom, and especially a neutral atom. I mean, the first trapping experiments that were done with atoms were not done with neutral atoms, but they were done with ions. So trapping a charged particle is a lot easier to do, kind of. So it depends what parts you're using, what parts are hard. But in principle, we can get started a lot easier with ions than with neutral atoms because, of course, ions are charged. And you can exert much stronger forces on charged particles than you can on neutral particles, just through electric fields. Once people started to trap ions, one of the things that was considered, well, when they're trapped, can we cool them? Why do we want to cool particles? Well, cooling is important if we want to do precision measurements. And a big part of atomic physics is about precision measurements. Some of the reasons we care about doing precision measurements are for fundamental physics. For example, we talked at the beginning of the semester that one of the very central topics in atomic physics is to try to, for example, measure very small forces like the fundamental forces of nature, tests of the standard model, tests beyond the standard theory of electroweak interactions. And in order to do that, we want to make the most precise measurements are possible. If the atoms are hot, it's a lot harder to measure them. So the colder they are, the less they're moving around, the more precise we can measure those atoms. From a technical point of view, those precision measurements, one of the most important applications of that is in the atomic clock. So a lot of the motivation for cooling atoms and ions was to make more precise clocks. In the context of the cesium standard for the second, that neutral atom, what limits our precision with which we can measure the frequency difference, the hyperfine splitting, which is the definition of the second, what limits that is how long we can do the measurement. Because you know there is a kind of uncertainty principle. If I want to measure a frequency, there is a limit to that uncertainty, which is related to the length of time with which we do the observation. So, and a very important motivating fact for trying to cool atoms was in order to, in the context of the neutrals, keep the atoms around long enough in a certain region of observation so that we can make a much more precise measurement of the frequency, and therefore, in that context, make a more precise measurement of the second. A similar kind of thing is true in ion traps. I mean, the ions are around, but they're still vibrating very fast if they're not cold. And that limits, if I'm going to use an ion as my precision, for my precision measurements, for doing my clocks, that too is a limitation. So the history of this is quite long, and I meant to bring with me, and I forgot, unfortunately, a list of some of the key dates. I can try to remember some of them. You know, I do know that the first, in 1975, there were kind of dual discussions about cooling with light forces. There was Ted Hench and Art Shallow talked about laser cooling neutrals, and Wineland and Itano for ions. There were two independent groups looked at this simultaneously. Around the same time, I think it was maybe 1978, optical glasses. Sticky optical field for damping atomic motion. And this stickiness, together with magnetic fields, led to what was known as the magneto-optic trap, which is now the workhorse of all cold atom, neutral cold atom experiments, affectionately known as the MOT. In fact, people call the group of atoms that come out of the magneto-optic trap a MOT. I have a MOT, it's this ball of atoms. That's the kind of jargon that is used today. And Komatsuyuki, together with Jean Dalibard, who was, I believe, his student at the time, really led a lot of the theoretical foundation. And together, these folks won the Nobel Prize in 1997 for the development of laser cooling and trapping. And soon after this work was done, one had a system in which the atoms were so cold, in fact, they were colder than were originally expected to be. I mean, this was one of the important theoretical contributions of Cohen-Tanucci and experiments out of Bill Phillips' group, so-called subdoppler temperatures that we'll talk about, that laser-cooled atoms became a starting point for evaporation to Bose-Einstein condensation. The idea that you could condense a gas into a Bose-Einstein condensate goes back a longer way. It goes back to Kleppner and Greytak, who were trying to do this with hydrogen gas, with traditional cryogenics. And it was tough. It didn't work. It didn't work, in fact, until after, in 1995, the groups of Carl Weinman and Eric Cornell at Gilla and Wolfgang Ketterle at MIT made the first BCs in rubidium 87. Art Ashkin thought about trapping neutrals in laser beams. Actually, what he was looking at originally was trapping little glass balls, little small particles or polarizable particles, but ultimately thought about this in the context of atoms. But the modern era where things have really gone started in the 80s. In the 1980s, there was a tremendous amount of work thinking about taking these ideas. This was Wineland and others were early pioneers in laser cooling of the trapped ions. But the work on the neutrals was much harder, happened a lot later. Not a lot later, but a few years later. And some of the key players here were Bill Phillips, our current Secretary of Energy, Steve Chu, and in the theory side, Claude Cohen. And Bill was the first to slow an atomic beam and then trap. And Chu at the time was at Bell Labs. You guys too young to know what Bell Labs is? Bell Labs, you know, it's sad to say this story about Bell Labs on the great industrial labs and transistor everything. I mean, Steve Chu was there working on, I think Ashkin was there at the time. I actually don't remember. It's before my time. But anyway, working on cooling and trapping atoms, and developed what was the first, what we call optical molasses that we'll talk about. How do you spell molasses? Are there two L's in molasses? Is that how you spell molasses? I can't.
There may be one
I
out.
think it's one L.
One L, two S's? One L, two.
One L, one, I think.
Is that right?
I don't believe it.
I don't know.
I think that
I'm
was-
sure about the L, I'm not sure about this.
We'll just leave it as such and don't remember. It's terrible. Someone must know. Anyway, so molasses was a kind of, a notion of a kind of sticky, this is